Oh, shit.
All right, it's 4 o'clock. Let's go get started. All right, good afternoon, everyone. How's everyone doing today? Good, doing good. All right. So we're end of week 6, and so we're very quickly approaching the midway point of the semester. Time's really been flying. Okay, so the plan for today is we're going to finish up our lecture notes on spinal biomechanics, and so there's not too much left to it, and so I have a couple examples, and then we can talk about spinal injuries after that. Okay, and so we might end a bit early today, and so that would be a good thing. And so today, right before lecture, I realized I forgot to post the solutions to homework 1, and so I went to go post the solutions for homework 2, and I realized homework 1 wasn't even up there, and so I posted both the solutions for homework 1 and homework 2, and so you should see them on Canvas now. And of course, homework 3 is out there right now. I've gotten a couple questions on homework 3, and so I think I need to double check some of my answers for homework 3, and so I'm going to do that after the lectures today. I have another class I need to teach right after this one, so I'll probably check it like around 7 o'clock today, and then you'll hear from me based on that. Okay. All right, and so right, so remember the midterm is next Thursday, and so we talked about it briefly on Tuesday, but remember it's an in-class midterm, and so you're going to have to be here in class to take it. In terms of the format, I've come up with the general format for the exam, and so let's just talk about that really briefly. And so for the exam, what I have is, because we've covered mostly a lot of conceptual information up until this point, the focus of the exam is going to shift a little bit more towards that. And so I have 6 short answer questions planned. Okay. And so those are very similar to the style that you've been seeing on the homeworks. And so, there will be 6 of those that you're getting to answer. And usually, for those ones, some people write a lot for those answers, and on the one hand, that's really good, and it's good to have detailed answers. But I designed these questions so that you can answer them in maybe about 2 or 3 sentences. Okay, and so these are going to be, it's going to make about 60% of the points. And then after that, I have two basically static biomechanical analysis type questions. And this makes up the rest of the 40%, the remaining 40% of the points. Okay, so that's kind of what I'm thinking of right now. So I'm about halfway done writing the exam, and so that's what it's going to be. And remember, for the exam, you can bring a single 8.5 by 11 sheet of notes. Okay, you can write on both sides of the sheet of notes. And I always tell people that, really take some time to work and develop on your sheet of notes, because just developing that and making sure you're taking good care of that by itself is already a great form of study, because we've at this point, after today, we'll have gone through 6 weeks of content, and to condense 6 weeks of content into a single sheet of paper, that takes a lot of studying that you need to do, because you need to read through everything that we've done, and think about what's the most important things to put, what's the most important pieces of information that we've gone over so far, and put it onto a single sheet. And so if you really kind of take the time to develop that, make it your own, write it out, make different sections on it and everything, I think that by itself is one of the best things you can do in terms of study. Because I know what some people like to do is they like to take my lecture notes and make it like teeny tiny and just put it all across the cheat sheet, which you can do that too. But I think with that, you you're going to spend more time on the exam trying to read the cheat sheet and see what's on it rather than actually doing the exam. And so, really take the time, condense the information, make a good cheat sheet, and I think you're going to be in really good shape for the exam. Question? All right, question. So the best thing to study are the homeworks and the study guide. Yeah, so definitely, I gave you guys the study guide, with the purpose, and so that's kind of the main thing I'm reading when I'm making the exam. And so if you understand everything on the study guide, you can answer all of those conceptual questions on the study guide. I'd say you're in great shape. And in terms of the problem solving type questions, if you can do the homework, so you really kind of understand, how to develop those answers, then that's something great for you to do as well. Okay. All right. So reminder, I haven't posted it yet, but I'm going to post today a poll. Okay. Okay. So I'm going to post a poll on the Canvas site where you can vote on the topics that you feel most uncomfortable with from the first part of the class. And then on Monday, I'm going to record a review video to help you study. Okay. So I expect the review video will probably be about an hour long. So it's not quite as long as a lecture, but because I don't want it so long that that you can't really watch all of it. But I want to make sure that I cover everything that you want me to in good detail. So you can expect the review video on Monday. Okay. All right, so I think that's everything. That's everything that I want to mention for the exam. Are there any other questions about the exam format or anything? Yeah. Are you going to collect the sheet notes? Probably not. Probably not. Any other questions on the exam? Okay. All right, and so let's go ahead and jump right into the lecture for today then. And so we're on our last section of the static biomechanical notes, which is your spine. Okay? And so last time, we talked about the general characteristics of the spine. We talked about the general anatomy, the muscles, how the vertebrae, bones are shaped. And so today we're going to be doing example problems. All right. So let me go ahead and start. I know we started an example last time, but let me go ahead and redraw it because I think I did a pretty poor job of drawing it last time. Okay. And this example is going to illustrate just how bad it is to lift up a heavy load with your back. Okay. All right. Myself a little more space here. There we go. That looks like a somewhat anatomically correct person's leg and behind. All right. So first thing I'm going to draw here is the muscle force, and so this is going to be our main point of interest here. So our muscle force is given by Fm. And the direction that it's pointing in is going to be defined by this angle theta m. And then right above here, we'll say this is the joint of interest. And then here we're going to have our joint reaction forces. And so we have Jy and Jx. Okay. All right, so let's draw the other loads that we're going to be concerned with. So first load that we're going to be concerned with is the weight of the leg. Okay. Okay, so the weight of the leg is going to be acting downwards. Okay. And then acting at the tip of the foot, we're going to have a combined force, which is the weight of your torso, so weight top, as well as the load. Okay. And so W underscore L, that's the weight of the load that the person's trying to pick up. Okay. And so I got a question at the end of class last time, but why do we put this load here on the foot? And the reason for that is we're doing kind of an approximate modeling here. And so, we're of course not modeling the entire body, but this part of the body is still supporting the weight of the torso as well as the weight of the load that they're trying to pick up. And so to kind of model that, we know that as those things weigh the person down, there's going to be equal and opposite normal force coming from the ground that's pushing up on the body. Okay. And so when we kind of cut off the top and we don't even consider the load, the load is probably somewhere over here, right? One way that we can do that is we can approximate it as just a normal force coming up from the ground. Okay. Next thing we need are going to be some distances. Okay. And so first distance I will draw here is the distance A. Okay. And so A here, A is the moment arm for the muscle force. Okay. And just for the sake of convenience, we defined it in a way that we don't have to consider any angles. Okay. And so A is perfectly the moment arm for that. Okay. Next distance that we need, so I took the joint and I just drew a dotted line down. Distance that we need here is the distance B. Okay. So B here is the moment arm for the leg weight. Okay. All right, and the last distance that we need is C, where C is the moment arm for the the normal forces on the ground. Okay. And so in this problem, just like we usually do, we have one muscle force and two joint reactions, and so we can solve this problem. And so let's go ahead and compute Fm, Jx, and Jy. Okay. And so just like we always do in these types of problems, we're going to form the equilibrium equations. And so we have the sum of the moments, sum of the forces, and then we're going to use that to solve for our unknowns. All right, so just to give some perspective, let me go ahead and give some numbers for these. And so we'll say the distance A here is 0.02 times h, where h is some reference distance. And so, it's going to cancel out, but, we can say that h here is maybe the length of the leg. Okay. The distance B is going to be 0.08 h. And then the distance C is going to be 0.12 inch. Okay. Okay. And for the weights, I'm going to define everything relative to the weight of the torso. Okay. Okay. And so we'll say the weight of the leg here is about 40% of the weight of the torso. Okay. So W leg is equal to 0.4 W top. W top is just W top because we're defining everything relative to that weight. And the weight of the load, we'll say is about 0.3 times the weight of the top. Okay. Right, and then finally the attachment angle theta m. Theta m is going to be 45 degrees. Okay. All right, so just like we normally do in these equations, the first place we're going to start is with the moment equation, right? And so that's typically what we solve first, because that will allow us to solve for the moment force. Okay. All right, so some of the moments around the joint. Let's go ahead and look at all the forces. And so, just because of the way that our moment arms are defined, we're not going to have to worry about any kind of angles here. Okay? So all the distances given are exactly the moment arms, just for the sake of convenience. Okay? All right, so let's look at FM first. So FM, relative to the joint, is going to be pointing in the clockwise direction, right? And so if you kind of follow FM around the back joint right here, it's going to push it. It's going to push a moment in the clockwise direction. Okay. And so the moment with respect to the moment with the muscle force is going to be negative. Okay, so we have a minus FM times A. Right. Next we have W leg, and so let's go ahead and follow W leg around the joint as well. Okay, so we follow W leg around. We can see that that's also going to be a clockwise moment, and so we have a minus W leg times B. Okay. And then finally, for the normal force on the ground, W top plus WL. If we follow this around the joint, we can see that that's going to go in the counterclockwise direction. So that one has to be positive. Okay. And so that's going to be W top plus WL, quantity multiplied by C. And of course, all of that has to equal 0. So let's go ahead and solve this equation for FM. So we have FM is equal to W top plus WL times C minus WA times B, all divided by A. Okay. Let's take this expression and we'll plug in the values for all our parameters here. Okay. All right, so W top, that's just going to be the same as W top. WL, we said was 0.3 times W top. C is 0.12 times H minus W leg is 0.4 times W top. And then B at 0.08 times H. And we divide everything by A, where A is 0.02 times H. Okay. And so we're just about done here. And so the last thing we need to do is just simplify this expression. And so we can see that we can factor out an H from the top, from the numerator, as well as the denominator. And so those are going to cancel out. Right? And then if we just do all the arithmetic, we add the H's, we add the W terms together, we divide by 0.02. What we get is FM is equal to 6.2 times W top. All right, so what does this result say? And so this result says that, if you're lifting a load that's, with your back and you're just kind of hunched over, then your muscle has to exert a force that's 6.2 times greater than the weight of your torso. Okay? Right, so that's pretty significant. And so, for a lot of people, their torsos make up, a pretty decent chunk of their weight. So, having a single muscle having to exert that much force is, is pretty big. All right, and so to kind of put some numbers on this, and so let's say that, let's say a person's torso weighs about 110 pounds. Which is not that much. And so this is about the average, somewhat average weight. And so this would probably be for a person that weighs somewhere between 160, 170 in total. Okay, so their torso makes up maybe a good 60% of their body weight. Okay. And so if a person's torso weighs that much and they were to lift, and if they were to try to lift a load of about 30, 35 pounds, right? So remember, we assumed in this example that the load that the person is trying to pick up is about 30% of their torso weight. And so in these situations, FM, the amount of force that the muscle have to exert is around 700 pounds. Right? Okay, so that's huge, and none of these numbers are that outrageous either. So 30 pounds is probably a bag of cat litter or something like that. And so if you were to try to pick that up with your back, your back, it has to exert 700 pounds. I used to live on a second floor apartment, and my wife would always hate to go get cat litter from the store, and so she would have it delivered. And every time the Amazon delivery guy dropped off like a big 30-pound bag of cat litter in front of our apartment, I was like, man, I feel bad for him to carry that up the stairs. And so, especially after I developed this example, like, man, that poor guy's back, man. But I'm sure he has back. I'm sure he's been taught in the proper lifting technique, so does get this back. Okay.
Amazon's famous for carrying.
Oh yeah, yeah. I heard they just gave everyone a raise at Amazon, so that's good. But I think it's still not enough. Okay. So let's go ahead and carry this through. So we're not quite done yet. So let's go ahead and compute the joint reaction forces. Okay, so this is pretty straightforward. So there's not much here. So I'm just going to go through it pretty quickly. So we have the sum of the forces in the x direction. So in the x direction, the only things we have are jx and fm sine theta. And so if we solve this for jx, we can see here that jx is just going to be minus fm sine theta m, which all that means is that jx is going to be pointing in the opposite direction. Okay. And so with these numbers here, we say jx is equal to minus 4.38 w top. And in the y direction, we have a little bit more. And so not only do we have the muscle force, but we also have the weight of the leg. As well as the weight of the torso and weight of the load. Okay. So, you can solve that through just algebraic manipulations pretty easily. And so if we solve for jy, we get minus 5.28 w top. Okay. Okay. So those are the joint reactions. Okay. So, first thing we notice that the joint reactions are going in the opposite direction of where they were. Okay. But let me do something, let me do one more step here that we don't normally do. So let me take the resultant of this joint reaction force. Okay. And so this is going to be based on the length of that joint reaction vector. Okay, so I'm just going to use the distance formula. And so I'm going to take jx squared plus jy squared, square root the whole thing. And so the resultant, or the magnitude of the joint reaction forces is a 6.86 w top. Okay. And so, even though it's already kind of alarming that the muscle force has to exert that much force, I think this is the part that actually is a lot more alarming, because these are forces being experienced by your vertebrate bones. Okay. Right. And so this is the part that's really scary, because, we talked last time about, some injuries that can occur at the back, one of those being a herniated disc. And so this is something that can cause a herniated disc, because if you compress your vertebrate bones together with, such a large amount of force, using the numbers that we had before, this is maybe around, 750, 780, pounds. That's something that can cause injury, and oftentimes is a fairly serious injury. And so this is the part that's kind of scary. So whenever you're doing anything with your back, you want to try to minimize that joint reaction force as much as possible, because this is the one that's can cause injury. But remember, keep in mind that this was lifting with poor technique. So, if you just kind of bend down with your legs straight and try to pick up that way, this is kind of the worst that can happen. All right. Any questions on this? Okay. All right, so let's go ahead and compare this. So let's do the same task, and so let's consider the same lifting task, but with good technique. And so the better technique is to, not bend down with your back, but to crouch down with your legs. And so that, first of all, your back is as straight as possible, and then you try to lift as much as possible with your legs. And so compared to the first configuration, this one's going to be a lot more bent down. Okay? And so by bending down, a few things happen. And so let me go ahead and draw this first. With my art skills, I need utmost concentration for this. The foot's weird, but it's okay. Okay, so just like before, we have our spinal erector muscles, and so it's going to be right here. So we have FM. First thing you should notice is that FM here is a lot more vertical than it was before. And so I think in the last example, FM was angled with about a 45 degree angle with respect to the vertical. Here, our theta is going to be much smaller. And so this theta here is only going to be about 20 degrees. Okay? So that's a lot more straight than it was before. And so that's going to help us out a lot. The same as before, we have our joint reaction forces here. So we have JY, JX. Okay. And then we have the different weights. So we have the weight of the leg. Same as before, we have our normal force coming from the ground. And so this is going to be W top plus WL. We're going to use the same convention as last time. And so we're going to define A, B, and C to be the following moment arms. Okay. Just to kind of make things convenient for us. All right, so another thing that happens in addition to the muscle force kind of straightening up, and so in addition to that being more pointed upwards, you also increase the moment arm for that muscle as well, just because that kind of sitting position, you have kind of more distance for the muscle force to act. Okay, and so our distance A here is going to be 0.03 times H. B is also going to get a little bit bigger because now your legs are kind of a little bit more in front of you. And so B here, we're going to define it as 0.1 H. And then C will keep about the same. And so C will still be about 0.12. Okay. Right, because your feet haven't really moved. It's just, you just kind of crouched in. And then all the weights will keep the same. And so we'll say W leg is 0.4, W top is equal to W top. And then WL is once again 30% of W top. And so same, all the same variables, it's just that now they take on, slightly different values because, we're crouched down now. Okay. And so the equations, because we define everything to be about the same way, our equilibrium equations are going to have the same expressions. And so, I'm just going to go through them quickly, but then you'll see the end result is that we're going to have a much smaller muscle force and our joint reaction forces are going to be much smaller as well. Okay. All right, so first thing I'm going to do is we're going to sum up the moments around the joint. Okay, so we have minus FMA minus W leg times B plus WL plus W top times C equal to 0. Okay. So FM is going to be W top plus WL times C minus W leg times B divided by A. Okay. So exactly the same as last time. And so, you know, that equation there is the same. The only thing that's different now are the values that we're going to plug in. So in particular, you know, the two things that change the most here are going to be B and A. Okay. But just by changing those two things, it's going to make a huge difference. Okay. And so if we plug in the values for everything here, we get FM is equal to 3.87 W top. Okay. So still, you know, fairly significant. And so, you know, anytime you have to lift up something heavy from the ground, you know, it's always going to be, you know, difficult, right? But this is much less than it was before. And so if you remember from the last, the last example with the port technique, we had a muscle force that was about 6.2 times W top. Now we reduced that down to not so much half, but maybe, you know, about 60% of the value that it was before. And so now we're about 3.87 W top, which is a really significant reduction. Okay. All right. And so let's go ahead and very quickly, let's do the joint reaction forces. And so if we sum up the forces in the X direction, we have JX plus FM sine theta equal to 0. Some of the forces in the Y direction, we have JY plus FM cosine theta minus W leg minus, or excuse me, plus WL plus W top is equal to 0. Okay. So we can solve these equations independently for JX and JY. And so from this, we get JX is equal to minus 1.32 W top, and then JY is equal to minus 4.54 W top. And just like we did in the last example, let's take the magnitude. And so we take the magnitude of the joint reaction. So that's square root JX squared plus JY squared. Okay. And then we get 4.73 W top. Okay. Both this and the muscle force are much lower than before. Okay. Any questions on any of this? Okay. All right, and so we can see here that, you know, when you lift with proper technique, you know, you relieve a lot of the stress, a lot of the tension on your back. Okay? And so, you know, let's take a moment and kind of break down what exactly was different about this one compared to the original one. And so the first thing is that the muscle force is a lot more vertical than it was before, and so it's not so tilted over. Okay. And so, you know, that kind of straightened that up. And because of that, you know, because the muscle force is pointed more straight up, and most importantly, away from the spine, or as away from the spine as much as possible, then what that also did was that it also decreased the, excuse me, it increased the moment arm for the muscle force. Okay. And so when you straighten up that back, and then you kind of tilt that muscle force away from your spine as much as possible, then you maximize that moment arm, and you make it so that the back muscle doesn't have to work very hard. Okay. Because the main thing, and we've kind of alluded to this a few times in the past, the main thing that's actually kind of pushing your vertebrae together and kind of causing a lot of joint reaction forces, it's not actually the load itself. And so the load itself actually, is not the main contributor to, pushing your vertebrae together. It's your back muscles. Okay. Okay. The weight is kind of, of course, the weight is indirectly responsible for that because, it's because you're trying to lift that weight that your back muscle has to work so hard. But, because the back muscle is because of the way it's because of the way it's kind of positioned in your body, it's almost parallel, excuse me, bless you, sorry. Because it's almost parallel to your spine, every time your back muscle has to contract, it's basically pushing the spine together. And so, a lot of ergonomics and a lot of, good lifting technique, a lot of that is going towards, how do we minimize the amount of work that the back has to do? Okay. Right, because if you look at the back muscle, if you compare its size to some of the other muscles in your body, your back muscle is fairly large, and so it's definitely not a small muscle, but it wasn't really designed to be carrying this much weight all the time. So and one of the other things too is that your back muscle is one of the muscles in your body that is almost always engaged without you really having to think about it. Your back muscle is the one that's primarily responsible for keeping you upright and maintaining balance. And so even though if you're not actively, telling your back to do something, it is still contracting whether you want it to or not. And so if you can avoid a lot of unnecessary stress on that back muscle, it's going to lead to, a lot less injuries. Okay. Any questions on any of this? All right. I have a somewhat funny story about this too. And so a few months ago, I would say maybe about 5 months ago, I was having really bad back pain myself. My friends had a ball with it. They call me old man and everything like that. But it got so bad that my wife made me go see a doctor. And so I went to a doctor, and then, first of all, he was super late. And so I got to the clinic really early, and then I sat in the room, the nurse let me in, and I sat in the room for an hour. And then the doctor finally came in. And then he asked like, oh, what's going on? So yeah, I have some back pain. And he said, oh, I looked at your vitals and it looks like you need to lose weight. I was like, did I really wait an hour for you to just tell me I'm fat? And so yeah. And so he said, you have to lose weight and then that's going to make your back better. And so since then I have not lost any weight, but my back is feeling better. And so take that, doctor. Okay. I showed him, that's right. I kept eating candy, and so now nothing can stop me now. Okay. All right, so this doesn't really have much to do with with our analysis here, but good lifting technique in general is good to know, because you're almost always going to be in a position like that. Whether you have a job that requires you to lift a lot of stuff, or maybe you're just doing stuff around the house. So and so even though the most advised way to pick up something is to lift with your legs, sometimes it's just not possible, just because you're in an awkward position or something like that. Okay. And so in those situations where you can't fully crouch down and lift with your legs, what people advise, that when you try to lift something up, try to keep your back as straight as possible. Okay. And so what doctors say is that, try to maintain as normal of a lumbar curvature as possible. Because like, as soon as you arch your back, and the more you kind of arch your back when you pick stuff up, what you do is you kind of maximize that attachment angle and you minimize that moment arm. Okay. And so by trying to keep your back straight, trying to keep a normal lumbar curvature, you maximize that moment arm and you minimize the amount of stress that your back undergoes. Okay. Okay. And so I have one more example that I want to cover today, just because this one's a little bit more relevant to your homework, and that's with workplace ergonomics. Okay. All right, and so it's really become a really big thing, I would say, in the last 5, 6, 8 years of designing the workplace to to work with the human. Okay. Okay. Because we kind of went through somewhat of a revolution, maybe 10, 20, 25 years ago, where we had a lot more people kind of working in office jobs. And what people were seeing was that even though these people were working relatively sedentary jobs where they're not really moving around, they're not doing heavy labor or anything like that, people were still sustaining a lot of injuries. Okay? And what people found was that even if it's not anything too severe, if you kind of subject your body to certain types of positions over long periods of time, it can cause injuries due to what your body has to do to maintain them. Okay? And so I'm going to do a simple example here. So let's consider just very simple, just the height of someone's desk. Okay. And so let's say you work at a job where you have to stand at a desk. Okay. And so the height of that desk actually has a big impact on whether you're going to have back problems or not. Okay. So we'll consider 3 different cases. And so in case one, we'll say is the best case scenario. And so in case one, someone can work at their desk. It's very appropriately heighted for them. Okay. And so they don't have to bend down at all. So they can kind of stand straight and do everything that they need to do, at their desk. And then from case 1 all the way to case 3, we'll lower the desk so that the person has to bend down more and more to do their work. And so one example for this would be like a chef. And so if you work in a restaurant, you work in the kitchen, you're kind of always on your feet. And so there's never a time when you're sitting down. And you're always kind of have to handle something in front of you. Either you're chopping something, you're cooking something on the stove, something like that. And so, it's really important in those situations that the workstation, where you have to work, is appropriately, designed for you. Okay. And so even though these three situations are different, they all have similarities. And so in all of these cases, the spinal erector muscles or your muscles in your back are going to have to engage in order to keep the person balanced. All right. And so we're actually going to analyze all three under the same diagram, it's just that we're going to change the numbers around a bit for them. Okay. Okay, so let's go ahead and draw the free body diagram. And note that in this case, we're not carrying anything heavy. And so in this case, the only thing or the only weight that we're going to have are just the person's own body weight. And so the weight of their head and the weight of their torso. Okay. And I'm going to exaggerate just for the sake of clarity. Okay. But this would be probably position of case 3. Okay. And so this line that I drew here, that's the line of their back, okay? And then this angle here, we're going to find that angle as the amount that the person has to bend over. Okay? Okay. So let's go ahead and draw in the muscle force first. So the muscle force we're going to assume is going to act right here. And we'll say that the attachment angle for the muscle force is going to be alpha. Okay. We have our joint reaction forces. And so here our joint reaction forces are going to be at the spine down here. And so I'm going to do these a little bit differently than before. And so normally we draw the joint reaction forces in the X and Y directions. Here I'm going to draw one component that goes right along the spine, and then I'm going to draw one component perpendicular to the spine. Okay. And so the component that goes along the spine, I'll call that JA. And so the A there stands for axial. And so that's a force that, that's pointing in the axial direction down the person's back. And then JS will be shearing, okay? And you'll see later on why I define it this way, just so it makes interpreting the results a little bit easier. Okay. And then we have our two weights, and so we'll say that we have a weight up here, so we'll call this W1, and then we have a weight right here, which we'll call W2. Okay. All right. And so since everything's on the same plane here, drawing the distances will be a little bit messy. And so let me do this instead. So I'm going to mark 4 points along this line. And I'm going to label them as points A, B, C, and D. Okay. And I'm going to give you the distances of each of the different, line segments. And so let's say that length AB here. And so AB is just the distance along the spine from the back joint to the first weight, W2. And so we'll say this is about 0.15 H. where again, H is some reference, some reference length on the body. So maybe it's the length of their leg or something like that, okay? AC here, so that's the distance along the back from the back joint to the muscle force, and so that'll be 0.2 H. Okay, and so of course this diagram is not to scale, and so the diagram makes it seem like FM is far away, but it actually is quite close to where W2 is acting. Okay, and then we have the distance AD, so this will be 0.3 H. Okay. All right, so now let's define the weights. And so we have W1. So W1 is the one that's at the very end. So this is going to be the weight of the arms, the shoulder, and the head. Okay. And for this problem, we'll say W1 is equal to 0.18 W. Okay. And so W by itself, we'll say that that's probably the person's whole body weight. And so what this is saying is that the head, the shoulders, and the arms, that makes up about 18% of the person's body weight. Okay. Okay. And then W2 will be the weight of the trunk. So that's just the weight of just your chest and your stomach. Okay. And we'll say W2 here is equal to 0.36 W. Okay. So as always, drawing these free body diagrams, takes a bit of time just because there's a lot going on, but hopefully this makes everything a bit clearer. All right, any questions on this? Okay. All right, so let's proceed the same ways that we used to, and so let's compute the muscle force first, and then we'll use that to compute the joint reaction forces. Okay, so for the muscle force, we're going to sum up the moments around the joint. So from this, just because we're running a bit low on time, and I want to make sure I talk about the injuries. It's a little bit longer than I thought today. So let me go ahead and write out the whole thing, and then we'll talk about it after that. Okay. Okay. All right, and so for the moment equation, remember what we multiply together are the magnitudes of the forces multiplied by the moment arms. Okay. And so for both the weights, W1, W2, the moment arms are going to be the length along the back times cosine of that angle, right? And so just like before, we can draw kind of a triangle like this. Okay. And the distance that we want on this triangle is this horizontal distance here. Okay. And so that horizontal distance is going to be the length of the hypotenuse multiplied by cosine theta. And so that's why we have those quantities there in that expression. Okay. Okay, so let's go ahead and solve this out. And so if we solve for FM here, we move all the non-FM terms to the other side. What we get is 0.15 W1 or W2, excuse me, cosine theta plus 0.3 W1 cosine theta all divided by 0.2 sine alpha, okay? Because all the h's here are going to cancel out. And let me just leave it in that form for now, because we're going to consider this under 3 different cases or 3 different values of theta. Okay? Case 1, case 2, and case 3. All right. Any questions on this? Okay. All right. So now that we have the muscle force, we can use it to compute the joint reaction forces. Okay. Okay, and so for these forces, we need to sum up the forces, because these joint reactions are not in the X and Y, we're going to sum up the forces in the A direction and the S direction. Okay. All right, so first let's sum up the forces in the A direction. So we have JA minus W2 sine theta minus W1 sine theta minus FM cosine alpha equal to 0. Okay. So here it's a little bit tricky because we have W1, W2. Those are vertical forces, but we want to find their components along the back in this case, and then perpendicular to the back. And so this is the components of W1 and W2 along. All right, so this is a little bit tricky to see. So let me go ahead and draw an image for you here. Okay. And so W1, W2 are the same because they're the same geometrically because they're both going vertically down. Okay. Right, and so if we draw W1, for instance, going vertically down, then what we can do is we can make a triangle out of this. Okay. Where this side of the triangle goes along the back. Whereas this side of the triangle right here is perpendicular to the back. Okay. And then the tricky thing here is to decide where the angle is going to go. And so in this particular case, the angle theta, the one that's given here, for the direction of the back, that's actually going to go at the top of the triangle right there. Okay. And so we can see from this figure here that if we want this component, we need W1 times sine. Okay. And that's exactly what we have right there. Okay. And so if we solve this equation for JA, what we get is JA is equal to W1 plus W2 sine theta plus FM cosine alpha right? And then let's quickly do the sum of the forces in the S direction. Okay, so we have JS plus W2 cosine theta plus W1 cosine theta minus FM sine alpha is equal to 0. Okay. And so if we solve this equation, we get JS is equal to minus W1 plus W2 cosine theta plus FM sine alpha. Okay. I know I'm going a little bit fast, but we are running a little bit short on time. So I want to make sure I get to the punchline for this, and then we just quickly talk about some of the injuries on the back. All right, but this is something that you can go back and verify yourself. And so, I definitely encourage you to look back at our in-class examples, verify that the equations are correct. Maybe catch a mistake I made. I make mistakes on these things all the time. Just so that you're kind of going through the practice in your head. Okay. All right. All right. Any questions on this? Yep.
What did you say was JS and JA?
Yeah, so JS and JA, those are joint reaction forces, except they're pointing in slightly different directions. So normally we do JX and JY, which is horizontal and vertical. Here we're doing JA. JA is pointing along the direction of the back. And so kind of the point of that is so that we can exactly see what the compressive forces are. Because JA is usually the one that we're worried about, because that's the one that's going to push your vertebrae together. And then the JS, the S there stands for shearing. So that's going to be anything that's pushing kind of perpendicular to the back that might be trying to misalign your vertebrae. So they're the same joint reactions as before, it's just that they're just in slightly different directions. Okay. Yeah, the reason I'm doing this is that because we're going to be modifying theta. And so remember, we started this example with these 3 cases here. And so, the direction for JA and JS are going to change each time, but, I still want them to tell kind of the same story. So that's why I have it just like that. All right, any other questions on this before we jump into the solution? Okay, so let's go ahead and compute all of these quantities for different values of theta. And so I'm going to summarize the results in a table. And you'll see that, even if we don't vary theta all that dramatically, it's still going to make a big impact on the results. Okay. And so in the best case scenario, this is case 1. Okay. In case 1, you're pretty much standing up perfectly straight. So in that case, theta is equal to 85 degrees. Case 2, you're not even tilting that much over. And so in case 2, we're going to say theta is equal to 75 degrees. And then in the worst case, we'll say that theta is 60 degrees. And so you're not even at a 45-degree angle, you're at 60 degrees, but you'll see it's going to make a big impact. Okay. All right, so let's start. I'm going to go across the rows. And so let's start with FM. Okay. And so you can see that even with a moderate amount of tilt, and so even of a 10-degree tilt, will change the muscle force from 0.21 up into 0.62. So that's almost 3 times as much force that your back has to exert just by tilting your back by 10 degrees. Okay. And of course, it gets even worse when you tilt it by 60 degrees. Okay. And then we can do the same thing for JA. So remember, this is the compressive force that the back joint is feeling. Okay. And so as you go from case 1 to case 2, it more than doubles the amount of compressive force that your spine has to exert. And so you can see why. And so this is the reason why I did JA and JS, because in all the cases, we're not really experiencing any kind of shearing force, and so JS is going to be 0. Okay? So the only thing that's happening is your spine is being compressed. Okay. And so these are pretty big differences. And so, imagine someone experiencing all these differences, 5 days a week, 40 hours a week, maybe even more so, considering how much people work nowadays. And so considering, if you have a desk that's too low for you, when you first get there, it may not seem like that big a deal, but imagine having to deal with that, for months at a time, and you're looking at, maybe a 3x, 4x, 6x difference in terms of, how much work your back has to do. And so, I think ergonomics is something I didn't really think about too much until I started getting older and I started getting back pains. But now I pay attention to it a lot. And so now it's something I'm really cognizant of, because I'm like, yeah, I sit at my desk, when I'm not up here lecturing, I'm sitting at my desk for like hours at a time. And so if I'm hunched over, that's going to make a big impact on how much pain I wake up with in the morning. All right, any questions on this? Yep.
You're young and slouch a lot. Does that affect your back going in the future? Or is it just kind of like when you get older and you slouch?
Oh yeah, it's you can definitely still hurt your back, even when you're still young, and that can have long-reaching consequences in terms of how flexible. Because remember we talked about before that there are these discs in between your spine, and so the more kind of stress you expose it to, even when you're young, you kind of degrade a lot of those, the structural integrity of those. You may not really feel it until you get older, but a lot of the habits that you develop when you're young kind of set up some bad stuff in the future. But I think even more importantly that when you're still young, you still kind of have the ability to correct your posture and make things better, and that's the thing that really sticks with you as you go older. And so what I've seen is that a lot of people that have bad posture when they're older, they kind of develop that in their youth, and then they didn't really take the time to correct it. And so that's the thing that really kind of hits you. Okay. All right. And so we have 3 more minutes. And so, I did want to talk quickly about back injuries, although I think, we'll probably save more of that discussion for Tuesday. So let me go ahead and share my screen here. Okay. And then, let's just kind of start talking about them, and then we'll talk about it more on Tuesday. Okay. Okay. So the first common injury of the spine is lower back pain. Speaking of back pain that I was facing. And so lower back pain is extremely common. So, some numbers and some studies out there say, close to 85% of the entire population experiences lower back pain at some point in their life. And so, it's something that's very common. And in terms of workers' comp, and so, people filing, for injuries that they sustain in the workplace, lower back injuries is by far the most common ones that occur. Okay. And so, lower back pain can be caused by a variety of cases, but we know that mechanical stress seems to play a big role. Okay. And, and we have kind of anecdotal evidence of this, because it seems to be a lot more common in jobs that require, to lift very heavy materials. Okay. But it's also becoming more common for people that sit for very long periods of time as well. Right. And so if you do have a job, even now as students, if you find yourself sitting for a long period of time, take that 10-second break to kind of stand up and kind of like straighten up your back, because it makes a difference. Okay? And so whether it results from kind of one big load that you lifted up, or maybe it's the cause from a lot of repeated cases, I think we're still kind of in the process of really fully understanding that. But there are a lot of cases where it kind of happens both ways. Okay. All right, fractures. And so I'd say fractures are not super common in the spine. And sometimes it usually has to have something traumatic has to happen where you have to sustain a very large impact. But it can happen. And just just knowing the crucial role that the spine plays in the human body, fractures can be very very catastrophic. Okay? So the most common place for you to sustain a fracture is in your cervical spine. Okay. And so that's kind of, remember, that's the very top of your spine. And the reason for that is, a lot of people sustain impact on the head. So if you hit your head somewhere, then that's going to damage the very top of your spine. So that's the cervical spine. Okay. And so stress fractures are also possible, especially if you're in a situation where you're kind of loading your back quite a lot. But they're not as common. But when you do have spinal fractures, they tend to be more difficult to heal just because of how the back is designed. Okay. Okay. All right. So I have a lot to say about herniations because I have some personal experience with that, and so we'll save that for Tuesday. And so any final questions on any of this? Okay, all right, so that's all we got time for today, and so we'll pick this up on Tuesday. You'll see on the study guide that spinal injuries are going to be part of the midterm, and so, I normally don't like to push content, the lecture before the midterm, but it's not that much more, and so we just have a couple more injuries to cover. All right, so thank you everyone for coming today. Hope you guys have a great weekend. Definitely be studying for the exam, and if you have any questions about anything, please don't hesitate to reach out. And so I'm available via email. You can set up an appointment. You can come talk to me any. Okay. All right, so I'll see you guys next week.
I got a question for the homework.
Sure.
So I know you asked us to draw the spine. Is it okay if I just put a picture
Yeah,
and
yeah.
label that?
Oh, yeah.
Okay, that's fine.
Yeah, yeah.
Okay. And then one other question was, I know you were talking about like spines today. How does that affect like the back? Because I know like the posture, like pulling at the side, like the spines like out. Is that also like the pressure points for the bed? Is that
yeah.
also affect the spine?
Oh yeah. No, sleeping positions, it has a huge impact.
Okay.
So, when you're sleeping, you don't think about it. 'Cause you're
Right.
sleeping a lot, but your body still has a subconscious kind of maintain itself.
Right.
And so if you have a heavy head that maybe you want to support sagging in there, that kind of has to compensate for more things.
Oh.
We have to kind of put a lot of acid stress.
Yeah, because it's like also like the positioning of your neck. That's like neck pillows. I see. Yeah. Oh, okay. All right. Thank you.
Yeah.
Yeah. Oh, yeah.
You need to move your desk.
Oh,
No, I said I didn't need to.
I didn't even notice.